Here the induced EMF has a magnitude L di by dt. One thing I would like to explain here, that this is the magnetic flux associated with each turn. If you are asked to write down the total flux associated with the coil, then you would have written phi equals to number of turns multiplied by phi 0. So the induced EMF is E equals to L di by dt, and from this equation I can write down L is E magnitude upon di by dt. Numericals are asked based on this formula, dear students, in examination. And we know induced EMF is joule per coulomb. So this will become joule per coulomb into ampere into time. What is the dimensional formula of joule? ml2 t minus 2 into time t. Coulomb is ampere into time into ampere. So I am left with ml2 t minus 2 a minus 2 as the dimensional formula of self-induction coefficient. Now my object is to determine this coefficient of self-induction for various circuits, and the most important among them is for a plain coil. Simple things are here. Let radius of coil is R, number of turns is N, then for current I, magnetic field will be mu naught Ni upon 2R. Area of the circular coil is pi r square. So flux associated with each turn is phi 0 is Pa, mu 0 Ni 2R into pi r square. Okay. So total flux associated phi will be number of turns multiplied by each turn, and that will be mu naught N square pi r upon 2 into I. Now I compare this formula with phi equals to Li. Compare it with phi is equal to Li. I will get L is equal to mu 0 pi r upon 2. This is how one can learn. Mu naught N square pi r upon 2 is the formula of coefficient of self-induction for a coil. And you can see number of turn doubled, coefficient of self-induction will be 4 times. Radius is doubled, it will be twice. But sometimes a very interesting question is asked: if length of wire used is small l, then what do you mean by L? Length of one turn into number of turn. So if L is kept constant, be careful, R into N is constant. So in many examinations it is asked that the same wire is wrapped over the coil to have the same radius. Then you should learn that L is constant, R is constant, then N will be constant. So no change in the coefficient of self-induction will take place. This is for a plain coil. Now I can determine for a solenoid. You know, magnetic field associated with a solenoid is mu 0 n upon its length L by number of turns per unit length. Consider there is a solenoid of turns n and length L like this. This is length L. Area of, so flux associated with each turn will be BA, that is mu 0 n upon L I A. So total flux associated will be NBA, and that will be mu 0 n square I upon L into A. So if I compare it phi equals to Li, the coefficient of self-induction L will be nothing, but it will be mu 0 n square A by L. This is the formula of coefficient of self-induction for a solenoid. I hope you understand it very well. And this formula gives you an idea that in both the cases the number of turns plays an important role. And larger is the number of turns, more will be the coefficient of self-induction. Here the area also plays an important role. Area A, the cross section of the solenoid. Larger is the area of cross section, more will be the coefficient of self-induction. And coefficient of self-induction I would like to tell you on the last page when I wrote the last formula. See here. Larger is di by dt, more will be the induced EMF. So when you close a circuit, the current reduces in a very small interval of time from maximum to 0. So what happens, the induced EMF is very high, and that sometimes can cause a damage in the circuit. This is what happens when you see that during the switching off a bulb, it gets fused. This is a very nice question which is asked in examination, that what is the probability of fusing a bulb during its when you switch it on or switch it off. Then your answer should be that during the switching off the bulb there is a chance of its fuse. Next time I shall tell you about the energy stored in a inductor. Thank you.